So the aim of this video is to go through some resources that you can download and also go through some practice questions and answers for the alkanes topic. So the first thing just to let you know is you can download an alkane summary sheet by using the link at the bottom of the page there. That will just take you to a document for you to download, and it just gives you the key points that we have studied. The first assessment that you could have a go at is an Alkanes quiz. These questions are pretty much they're quite straightforward. Just to test, do you know the material? Do you understand it before we start thinking of applying it? And again, you can download that quiz by following the link at the bottom. Once you've done that, you can check your answers by carrying on with this video. And the other assessment that you can do, these are more complicated exam style questions you can have a go at. And again, you can access those by following the link on the page, and the answers will be towards the end of the video. So first of all, we're going to go through the alkanes quiz. So we're going to look at 2-methylpentane. First of all, they want its molecular formula. So remember, the general formula for an alkane is going to be CnH2n plus 2. So that gives us C6H14. And the structural formula I've shown there in blue, along with the displayed formula. Don't forget on the displayed formula to show all the bonds. It's very tempting at this stage when you're in a hurry to show that group there as just CH3. That would not be classed as displayed. Skeletal again I've shown there. Question 1 is quite straightforward. For question 2, we're looking at boiling points, and we just want to first of all arrange those alkanes in order of increasing boiling point. So first of all, we start with butane, followed by pentane, and then hexane. And the reason why is because, of course, butane's only got 4 carbons, pentane's got 5, and hexane's got 6. So the carbon chain length is increasing, which means the surface area between those molecules increases. So we have more surface contact, which increases the strength of the London force between the molecule, which requires more energy to separate them. So it's really important that you always link that to the strength of London forces and the energy required to separate them. Very similar question for B. This time we're just looking at isomers. So these all have the same molecular formula. But you can see that the 2,2-dimethylpropane is far more branched, then followed by 2-methylbutane and pentane. So I've drawn the molecules there at the top in that order, so you can see. So obviously that's 2-methylpropane, that's 2-methylbutane, and this one is pentane. So as these try and pack close together, these guys cannot pack as closely together as these guys. As you go across from 2,2-dimethylpropane to pentane, the branching decreases, the molecules can get close together, which increases the points of contact between them and increases the strength of the London forces. And now this little question here, number 3, does catch quite a lot of people out. Alkanes are saturated hydrocarbon. Explain what that means. Well, you need to explain both the term saturated and a hydrocarbon. So saturated means they contain only single bonds, and hydrocarbon means they contain only carbon-carbon and carbon-hydrogen bonds. So a couple of goes at balancing equations now. First one is for complete combustion of methane. So that means we form carbon dioxide and water. So you get a mark for getting those products right, and then you just got to balance that out. And then the incomplete combustion of ethane, the difference is, of course, that we will make carbon monoxide rather than carbon dioxide. Now, balancing these equations can cause people some problems. It's actually quite straightforward to do this. So you've got 2 carbons there, which means you must have a 2 there. You've got a 6 for the hydrogen, which means you have to have a 3 in front of the water. And then you count out how many oxygens you've got on the right hand side, where I have 5. And so it's going to be 5 divided by 2 for the number of O2 molecules. Moving on to question 5 then. This is of course an example of free radical substitution, and the bond breaking is homolytic, which means the bond breaks evenly. So one electron goes to one chlorine and the other electron in the bond goes to the other chlorine. You need UV light to do this, and then I've just given you an example of an initiation step, the 2 propagation steps, and 3 examples of termination steps. You only require 1, but any one of those 3 would be fine. So we move on to Alkane exam style questions now. So these will be slightly more difficult because these would be the type that you will expect to see on the actual paper. However, start quite straightforwardly. General formula of an alkane, that should be okay. And a definition. Got to learn those definitions perfectly to get those marks. Then we're going to name isomer C. You can see your longest carbon chain length there is here. So that's 3 carbons, propane, and then carbon number 2, you've got 2 methyl groups. And we've already covered this in the quiz. Why does the boiling point vary? So hopefully you're okay with that one now. Right, moving on to the next one. Why are alkanes unreactive? Well, alkanes are unreactive because carbon-carbon bonds and carbon-hydrogen bonds are very strong, so it's difficult to break them apart. And also they're non-polar, so they will not really be attracted to anything else to attack it. For example, later on we look at nucleophiles and electrophiles, so that's the reason why. This is a flashback to our previous topics. The shape around a carbon atom is going to be tetrahedral. This is, of course, we'll know because you've got 4 bonded pairs of electrons and they repair equally. How would it be different in cyclopropane? So cyclopropane is going to look like that, and then you'll have hydrogens coming off like so. So this is basically, well, it's a triangle, isn't it? And so your angles here are now going to be 60 degrees. So your bond angles are going to be much smaller. So this molecule is obviously quite unstable and it is reactive because those bonds are so strained. Right, so back on to free radical substitution then. And we've got, again, going to show chlorine breaking apart. Radical is a species with an unpaired electron. Again, that's one worth knowing. We've put some dots there to just show where the free radicals are, and you will see them there, those 4 there. Why is it a chain reaction? Well, it's because this chlorine free radical here, which is used in step 1, is regenerated in step 2. This is the overall equation there. You could, of course, produce a different isomer if you wanted to by putting the chlorine on the middle carbon. And all 3 possible termination steps are shown there. You basically take any of your free radicals that you've generated up here and combine them together. So you could combine 2 chlorines together, 2 of those together, or 1 of those and 1 of those together to give you your 3. So we're going to now look and think about how cyclohexane, which I've drawn on the right hand side there, reacts with chlorine. How many, with UV radiation, how many di-substituted halocycloalkanes can I make? Well, okay, let's put 1 on there. So the other one could go there. So that would be 1. However, it could also go there, 2, could go there, 3, or it could go there, 4. If I start going back around again there, like so, that is of course going to be exactly the same as the one opposite it. So that wouldn't count because these 2 are effectively the same in relation to that chlorine there. So you've got 4. And then finally, why do we avoid using free radical substitutions? We've learned all about them. Why don't we like using them as chemists? It's because, as we've just seen in C, you can get multiple projects produced and then they all have to be separated, which can be very time consuming and very expensive. So free radical substitution reactions are to be avoided if possible.